Every 18 minutes from now, somewhere above the southern sky, a quiet voice will check in. It will click on, say one clean note for about a minute, then go silent, then click on again. And in the gap between those two notes, the entire field of radio astronomy holds its breath. We have been listening to this signal since 2018, and we still cannot tell you what is on the other end of the line. If you are the kind of person who would rather hear a real cosmic mystery than a movie trailer, you are in the right room. This channel is run by people who chase the slow, strange beats of the universe and tell the story exactly as the data allows. No movie magic, no jump scares. Hit subscribe so the next tick of this cosmic clock does not pass you by. To understand why a slow repeating radio signal can quietly freak out a whole field of scientists, we have to start with how scientists listen to the universe in the first place. Radio telescopes are giant metal ears pointed up at the sky. They look like enormous white bowls, sometimes as wide as a football field, and most sit on flat, dry land far from big cities because cities are loud in radio and the dishes are trying to catch whispers. Most of the time, scientists are listening for steady, boring signals from things like pulsars, quasars, and big clouds of hydrogen gas drifting between the stars. Those signals follow the rules. They are predictable. They are like listening to a clock that has been ticking for 100 years and always reads the same time. But once in a while, an ear pointed up hears something that does not fit the clock. A brand new beat appears that nobody put on the wall. And when that happens, calm scientists get a wide-awake look on their face. That is because in radio astronomy, anything new is usually either a known object doing a rare move, or it is a brand new thing that no one has ever seen. The signal we are about to talk about is firmly in the second camp. To start that story properly, we need to go back to a quiet stretch of red desert in Western Australia where a giant array of small radio tiles called the Murchison Wide Field Array listens to the sky day after day, year after year. The lead researcher on the discovery was an astronomer named Natasha Hurley-Walker, who works at Curtin University in Perth and at the International Center for Radio Astronomy Research, which most people call ICRAR. Her team was sifting through a large sky survey called Gleam-X, a giant radio map of the universe that takes weeks to load on a regular laptop when one source kept beating like a heart on the chart. The team gave the source the long code name Gleam-XJ162759.5 which is just the sky coordinates written in math. Most of the time, scientists just call it Gleam-XJ1627 for short, like a nickname. Here is the part that matters. The pulse was bright. It lasted between 30 and 60 seconds, longer than most flashes from space that scientists were used to. And then it came back after a wait of exactly 1,091 seconds. That is roughly 18 minutes. Scientists expected a brand new source to look messy, like static, like the universe dropping a pebble into a pond. Reality was the opposite. The pulse was clean. The pulse was steady. The pulse was almost too tidy, like someone had wound up a toy and set it on a windowsill. Why this matters is that clean repetition is a property of very few objects in space, and every single one of them is already in the textbooks. This object was not in the book. After the discovery paper was accepted for publication in the journal Nature in January of 2022, the strange source was everywhere in the astronomy community. People ran to their notebooks. People ran to the whiteboard. Why this matters is that every natural object we know about that pulses with a regular beat is either a spinning dead star called a pulsar or a hypermagnetized dead star called a magnetar. Pulsars spin fast, sometimes hundreds of times per second. Magnetars spin slower, but still many times per minute. Both of them are neutron stars, the leftover cores of giant stars that exploded a long time ago, and both are about the size of a city but heavier than our sun. The trouble with Gleam-XJ1627 was the beat. An 18-minute beat is way too slow for any known neutron star to spin in real life. Something was wrong with the simple answer. Did you know that Gleam-XJ1627 went from a quiet line in a giant data file to the cover of science magazines in just a few months? If you were the lead scientist on the paper, would you have rushed the discovery out the door or sat on it for a year until every number checked out? Drop your answer in the comments and tap like if you think this story has more chapters left to write. Now let us step back and look at how big this beat really is. The fastest known pulsars spin more than 700 times every single second. That is like a top spinning so fast you cannot even see it with your eyes. Magnetars spin slower, often once every few seconds. Even the slowest known neutron star takes only dozens of seconds at the outside to complete one full turn. 18 minutes per turn is something totally different. That is the speed of a slow ceiling fan, not the speed of any star core. So the very first part of the puzzle is that the thing we are seeing, whatever it is, should not be spinning at all based on what we know. Something else must be calling the shots. In everyday language, an 18-minute beat is longer than most sitcom episodes. It is longer than a coffee break. It is longer than a slow song on the radio. Yet this object in space was opening its mouth, saying hello in a clean radio note, waiting 18 minutes, saying hello again, and doing that with machine-like patience. Scientists at Curtin University and ICRAR called the object the first of its kind and asked the rest of the world to help them figure it out. Scientists expected that any natural explanation would also come with a visible counterpart, meaning telescopes looking for ordinary light at the same spot. would see at least a dim star, a flickering star, or at the very least a tiny dot of something glowing softly. Reality was the opposite. When pointed optical telescopes, including some of the best ones in Chile and in Earth orbit, looked at the spot where the radio signal came from, they saw almost nothing. The signal was bright in radio, but nearly invisible in ordinary light. That is strange. Stars are usually bright in both, so whatever was calling out was doing so almost only in radio waves, like a person humming in a quiet room with the lights off. Why this matters is that Gleam-XJ1627 quietly broke two expectations at once. It broke the speed limit of spinning neutron stars, and it broke the brightness pattern of normal young stars. That is how scientists began to suspect that the answer might not be a known thing, but a brand new kind of object. That is how a brand new phrase entered the astronomy vocabulary, the phrase long-period radio transient, because the object was a category of one, with no friends, no family, and no home in the textbooks. And here is the next part of the story, the part that people remember most. In 2023, only about a year and a half after the first discovery went viral in the astronomy world, a second long-period radio transient showed up. This one was found by a different team using a different telescope in South Africa called Meerkat, a giant array of 64 dishes working together as one. The new source was named GPMJ1839-10. Scientists expected this second object to look pretty similar to the first one because usually brand new classes of objects come in groups that act alike. Reality was the opposite. GPMJ1839-10 pulsed once every 21 minutes, far slower than even the first object. And the signal was louder, more energetic, and came from a different part of the sky. To put that 21-minute beat in everyday language, it is longer than a sitcom episode, longer than a coffee break, longer than a slow song on the radio. Yet this object in space was opening its mouth, saying hello in a sharp radio note, waiting 21 minutes, saying hello again, doing that with machine-like patience. Scientists at the Max Planck Institute for Radio Astronomy in Germany, who were also part of the team, called GPMJ1839-10, the longest period magnetar candidate ever detected, but they also admitted the magnetic field answer did not quite fit the data. The mystery was piling on top of itself like a tower of soft bricks. Now here is where the story takes another strange turn, the kind that keeps scientists awake on a Saturday night. In early 2025, a fresh team led by researchers, including a young student named Y, men went back through 3 decades of old Australian telescope recordings, the kind of tapes you would find in a basement, and asked one quiet question. Has GPMJ1839-10 actually been blinking at us all along, just quieter than we ever noticed? The answer that came back was shocking. The object had been pulsing for 30 years, almost since the time the World Wide Web was getting started in the late 1980s. We just were not looking with the right kind of instruments to see it. For 3 decades, the universe was humming a slow song into a microphone that nobody had plugged in all the way. The song was always there. We just finally turned the volume up. Why this matters is that GPMJ1839-10 is not a tiny fluke. It is not a one-time flash. It is a 30-year-long steady rhythm hidden in plain sight. That is the kind of evidence that turns a strange curiosity into a brand new branch of science, and every new piece of evidence makes the question louder. What kind of object in space can keep a clean 21-minute beat going for 3 decades without ever running out of fuel? Did you hear that GPMJ1839-10 sits roughly 15,000 light-years away from us in the direction of a small constellation called Scutum? That is almost halfway across the Milky Way, the kind of distance where the light we are seeing left the object back when our ancestors were painting cave walls. Would you guess that something halfway across the galaxy is easier to explain or harder to explain than something near us? Comment your honest reaction below and tap subscribe if a 30-year cosmic heartbeat sounds like a story worth following. Now let us talk about the theories, because the theories are a story of their own. Every working idea tells us a little about what scientists think is most likely and what they think is least likely. The first big idea is the magnetar theory, which says these are magnetars whose slow beat is not the spin, but rather a slow wobble. The kind a spinning top makes right before it falls over, also called precession. Magnetars are real. We have found them. They send out giant flares now and then. Trouble is, the math does not quite work out the way scientists hoped, and the model still has open ends. The second idea, the one most scientists talk about right now in 2026, is the white dwarf binary idea. White dwarfs are the leftover cores of normal stars like our sun after they have finished burning their fuel. They are about the size of Earth, but carry most of the mass of the original star. We have caught white dwarf pulsars before in other wavelengths, but never one that pulses in clean, bright radio. If Gleam-XJ1627 and GPMJ1839-10 are white dwarf systems, the field has just grown by a whole new kind of cosmic lighthouse, and the math actually fits the slow beat better. White dwarfs can comfortably spin on the order of minutes the slow way. They can also live for millions of years without running out of fuel. That would explain why GPMJ1839-10 has been pulsing for 30 years without fading. The third idea, and the one with the most votes in the room right now, is the binary interaction idea, posted by teams at ICRAR working with Meerkat data In this model, the slow beat is not the spin of one object, it is the gentle slide of two objects orbiting each other very slowly, like two ice skaters holding hands at the center of a frozen pond. Each time one of the skaters passes through a part of the dance where the magnetic fields are strongest, a clean radio pulse fires out toward Earth. Why this matters is that this is the first working model that lets ordinary astrophysics fit the slow beat without bending any rules. And in late 2024 and into 2025, follow-up observations with the Meerkat Array in South Africa started to show hints of a faint partner nearby, like a small warm companion tucked behind the bright voice. The jury is still out, but the binary idea is now the most popular contestant. And right now, today, in the middle of 2026, this story is not finished. New long-period radio transients are being found in the data from old telescopes that have been collecting radio waves for years. The Murchison Wide Field Array in Western Australia keeps finding new ones. Meerkat in South Africa keeps finding new ones. By 2025, two long-period transients had been conclusively identified as white dwarf plus small red dwarf binary systems, which is what scientists call WD plus M dwarf binaries. In 2026, a brand new long-period transient nicknamed the Unicorn, with the long code chime J1634 plus 44, appeared in the data from the CHIME radio telescope in Canada, the same machine that finds fast radio bursts. It expanded the family and challenged the existing models in one move. The count is climbing, the list is growing, and every year the slow beat at the heart of these objects gets a little less weird and a little more ordinary in the way science often works, one observation at a time. Here's something I want you to hold on to for the rest of the night. These objects are not rare because they are small. They are rare because they are slow. Most radio telescopes were built to catch fast things. We built our instruments to match the things we already knew about, so we may have been missing slow cosmic heartbeats hiding right in front of us for decades, just like we missed GPMJ 1839-10 for 30 years. That is not a small thing. That is a quiet change in how we look up at the sky. And here's what scares even the calmest scientists about all of this. The slow beat is too slow for any known neutron star. The signal is too clean in radio for most natural sources. The visible counterpart is almost invisible to ordinary telescopes, and some of these objects have been humming steadily for longer than many human generations. Every working answer has a missing piece. Every confident headline has a soft footnote. That is the rarest kind of mystery, the kind where the data is strong and the explanation is soft. Let us zoom out for a moment. What does this mean for us on Earth? First, it means the universe is being kinder to us than we thought. It is giving us slow, patient signals that we can study calmly instead of one-time flashes that disappear before we can blink. Second, it means our search for life in space may have a brand new clue hidden inside it. Some long-period transients still get joked about as possible alien beacons in online astronomy chat rooms, even though there is no real evidence for aliens at the moment. Why this matters is that the joke itself tells us how strangely clean the data looks. Third, it means the future of radio astronomy is being rewritten in real time, with new telescopes and new pipelines being built specifically to look for these slow, thrumming signals. The hunt is on, and it is louder than it has ever been. And here is the deeper thought that makes this story feel personal. We have spent decades scanning the universe for fast signals, fast radio bursts, fast spinning dead stars, fast laser pulses. We have built our eyes for the quick beats, and our eyes have been missing the slow beats even when those slow beats have been playing right in front of us 3 decades in a row. And that is a quiet reminder that even a field as serious as astronomy is shaped by the tools we choose to build. Future generations will not see the same sky we see because they will be holding different ears up to it. So what scares you more right now than the idea that something in space can keep an 18-minute beat for 30 years, or the idea that we may have been missing similar slow songs in plain sight for much longer, hidden in old data we already had on the shelf? Drop your honest reaction in the comments below. Share this video with a friend who loves a slow-burning real mystery, the kind that keeps unfolding quietly while nobody is watching. Turn on the bell so you hear about the next strange radio tick the moment it gets announced by a team on the other side of the planet. And if you want to be the first in your group chat to know when a brand new long-period transient gets a nickname, hit subscribe now so we can stay tuned to the same cosmic beat together. Thank you for spending some of your night with us listening to a slow song the universe has been humming for 30 years. We will see you next time.